As you may know now, I'm Gianluigi Rozza, and it's a pleasure to introduce the next speaker, Dr. Boris Kramer, from the Department of Aeronautics and Astronautics, Aerospace Computational Design Laboratory of Massachusetts Institute of Technology. Boris is working in the group with the Professor Karen Wilcott after a PhD at Virginia Tech with Professor Barnes. And his research program is focused on computational methods, numerical analysis for control optimization, design and uncertainty quantification of a large-scale dynamical system. And the title of the talk he's delivering is Conditional-Value-at-Risk Estimation with Reduced Order Models.
Thank you, Gianluigi. Thank you for the organizers for putting this together. A really great opportunity, and thanks for having me as a speaker. So today I want to talk a little bit about conditional value at risk, which is a special sort of a risk measure, how to estimate it, how to compute it efficiently. And I'm very interested from my research background in reduced order models. So we kind of wanted to see where we can use information from reduced order models to estimate these conditional value at risks. This is collaboration with my postdoc advisor Karen Wilcox, with Matthias Heikenschloss at Rice University, and his former PhD student and now postdoc at Lawrence Berkeley, Timur, Dr. Gadnov. And then want to acknowledge some funding. And so first I want to start with about maybe a few slides just to motivate the problem. Why are we interested in computing conditional value at risk for engineering applications? And then in the second and third parts of the talk I'll go into how the methods we proposed here. So as I don't have to mention much here, but optimization under uncertainty can be expensive. It, especially if you work with large-scale models. The cost functions typically, if you want to sample a cost function you're trying to minimize, require samples of an expensive high-fidelity model. You often need many of these samples for a meaningful evaluation of your cost. And if you're moving into more of the tail regions of something you could call tail risk, then the problem becomes a little bit more challenging, even more so, and efficient sampling approaches are needed. So I'll structure it in 4 parts. I actually decided to put the test problem right at the beginning, so I can go along and, as I have some results, I'll also show both theoretical and numerical results a little bit mixed up, so hopefully it makes for a good flow. And then in the second, third, and fourth part, I want to show you 2 different scenarios. One of them is we have a reduced order model and we're able to get rigorous error bound on this, like the reduced basis methods, for which we've seen very nice talks about. And then in part number 4, if we don't have that, then how can we still use surrogate models efficiently to give us an information about sampling in CVaR? Okay, so just to set the notation here, I call this first of all, I define my probability space. I have m parameters that have a certain density, rho here, that I'm interested in. And then I have my nonlinear system that depends on I know notation is flying all over the place, depends on different communities, but for now I use y as my state vector, or as my state solution. Psi is my xi is my parameters, and then z is my control here. And I also know this is a topic that's interesting. We assume here that our control is a deterministic control. There's different modeling assumptions you could make, but we say here that the control would have to be decided before I observe a realization. Okay, and then this is what I need in a couple of slides. I have an output quantity of interest. This output acts on my state, and I call it S. So a general framework to formulate this risk-averse optimization would be you're trying to find a control or the input set that minimizes some sort of a cost function, and I denoted it with R because I want to call it a risk measure. And then you have some penalty, and Martin introduced that in the talk before. You would have some penalty on the control term, and of course a lot of this and everything is of course subject to the solution of an expensive high fidelity model here. Now of course, there's many modeling choices. How do you want to embed your risk aversity? And there's different ways of defining these R's. Before we had something, the classical control setting where you have y minus a reference signal that you're interested in or a target signal. Here we're looking at a couple of different measures. So essentially, when I try to minimize that, that's what I'm trying to show. In every iteration that you're trying to find the control in this iterative process, you have to sample your risk measure, and your risk measure depends on random parameters, so you have to do some computations. A couple of ways to look at this. So you have different ways, and I use risk measure loosely now. So this doesn't have to be a coherent risk measure for now. But you could say, okay, I'm interested in minimizing the expected value. That's one choice you could do. Problem is you have, and all of these risk measures, they're modeling choices. So you pick a risk measure because you're interested in achieving a certain goal, and all of them are very valid. We just look at and it really depends on what you're interested in minimizing. So expected value is great, but you don't have much information about the deviation of your quantity of interest. Then some people you can propose to use the mean plus the variance, which is you have your mean term and you have the variance. That's actually great. It works for a lot of problems. But one thing is it equally penalizes lower and higher than expected costs. Question is this what you want to penalize? You can also do things like the mean plus the upper sigma deviation, which just mean you cut out the lower cost and you say, well, I want to penalize everything that's higher than my mean. Okay, it's a reasonable choice. People do that too. And with the, by the way, with a plus function here, we just take the maximum of zero and the argument. And then there's a class of other interesting risk measures. One of them being called the conditional-value-at-risk. So now I just make a quick notational setting that I'll simplify for the rest of my talk. So I call x of xi my quantity of interest, my output quantity of interest, and that's the output acting on the state and the parameters. So this is, I'll use x of xi for the rest of the talk. Okay, and so now we have to compute, for example, this value at risk at the level beta. You can think of this as a quantile. And beta is often in these applications we're looking at where beta is mostly around 0.9, 0.95, 0.98. These are the kind of values you can think about that we're interested in computing these quantiles. So then you would have what's called the value at risk, which would be just this infimum, and it's essentially your beta quantile. And looking here, you have a CDF, so a cumulative distribution function of our quantity of interest. So you would find if you set your level, I think this one would be the, if you set beta 2, then you get your quantile here. And now you can define something else, which is called the conditional value at risk. If you say I'm not really interested just in this value at risk, but I'm interested in everything that happens in the tail and happens after, you would want to integrate from the value at risk onward, meaning you're interested in the tail behavior. Number one, it matters how long the tail is, and because you can incur a lot of risk up in the tail. And so that's what Rockefeller and Uriasov in 2000 proposed and called it the conditional value at risk. Nowadays, people also call it the beta superquantile. So you can choose your terminology. And it's essentially the value at risk plus an integral over the tail. And this one is particularly interesting because it penalizes rare outcomes. And like I said, the length of the tail matters. And we're interested in this one for engineering applications. And again, there's a couple of really interesting. First of all, there was a talk on Tuesday, which I unfortunately missed, from Abdul Latif Haji Ali on multi-level Monte Carlo methods for efficient risk estimation, which is motivated, from what I understood, in finance applications. So there's a lot of work. If I was to put finance applications here, I would need a couple slides. So a lot of work in the financial community to insure against extreme losses that you would have in a portfolio. So that's where it really took off. But recently it also has found some attraction in the engineering community, and there's just a few papers I cited here that are most recent and really look at very nice optimization under uncertainty. This is one of Royset, who has done a lot of work in this area on the hydrofoil design for ultra high speed vessels. noise reduction by Max Gansberger on a turbofan engine. The typo. Forest fire detections goes back to Morio in 2012, and then some physically motivated advection diffusion problems by Khoury and co-authors. So there's recently been a lot of interest in using these because it kind of gives you a robust design. So they're often used also for design problems, and therefore the problem becomes all of these computational the systems that people look at are pretty expensive. So how would you go about efficiently sampling when you have an expensive model? The test problem I'm going to look at today is a nonlinear problem. So it's going to be a convection diffusion reaction problem with it's a simplified model of a premixed combustion flame. It's one reaction that's in there, and then we have a couple of, so you have convection diffusion and your reaction terms, nonlinear of Arrhenius type. And what you do here, you have these pre-exponential coefficients, and you have your E parameters in here. And now I'll treat two parameters in this model. So this is a typical state snapshot. We have inflow condition. I didn't mention that. We have an inflow condition over here where a mixture, a premixed, mixture comes in here, and then it starts burning off. You see temperatures are going all the way up to 2,400, I think, in this case. And then we have like cooled walls here and around. Okay, and so again, these in talking to people, these rates like A and E are uncertain. We'll treat them as uncertain parameters, and so now we kind of have a nice setup for our problem. So we have uncertain parameters that I want to have these two reaction constants that I need in my reaction models. I have so now we're going into the discretized world. We have a finite difference discretization of our model, which gives us a nonlinear system to solve. And then my quantity of interest is, in a sense, my quantity of interest penalizes temperatures above 2,000 degrees. So I mean, I don't want my combustion or the temperature to get too high in the domain with a certain scaling factor. So you see here the values of the maximum temperature. So over parameter space, so if this is my E parameter, this is my A parameter, and you see for two parameters, I'm going to run my solution, and then I get pretty hot fields around here. Now if I do the scaling, meaning if I define my quantity of interest, the map looks like this. So high values are kind of in this bottom corner of the computational of the parameter domain, and colder values are over here. Okay. And so for this quantity of interest, I can also just plot the cumulative distribution function of x, which has a value at risk of, I think, about, so everything is scaled here, of about 42, 43, and the conditional value at risk, I think, is 54. So that's how you would get that. And so now I want to add some additional information to the problem. I essentially want to say, how can we efficiently leverage all the information we have about this problem, for example, in form of surrogate models? And you could think of different ways of modeling surrogates, but we here are using a standard POD, empirical interpolation, or discrete empirical interpolation method. So we would have a reduced system that we obtained by some projection, by some reduced order modeling of our original dynamics or of our original model. And this is fairly coarse, so we're using only, this is a fairly nice system. So we have 4 different reduced order models that I'm looking at with different POD basis functions. And now I can define my surrogate quantity of interest, which is the quantity of interest that my surrogate model gives you, as the following. As the max temperature of the surrogate model, same scaling out as well. So now we're looking at errors. So these are just errors computed on a spatial grid. So I can do the error of my first reduced order model is pretty large. If you can't read it, this is about 800. So it's very, very high. This is a total garbage model, actually. Then I have in the order of 25 here, in the order of 0.9 here for the fourth reduced order model. So we're trying to say we have different models of different fidelity. The first one is pretty bad. No one would. I wouldn't use it just as a surrogate model itself. But the point I want to make later that some information can still be valuable, and we'll see how we use that, okay? And then I show you 3 ones, and I have a 4th one as well. And so now I want to say, in the first part I say, okay, how can I directly sample on my reduced order model? That's pretty cheap, because the reduced order model is thought of like almost free to evaluate, so you don't have to, there's no cost to evaluate the reduced order model, or very negligible cost. Haven't told you how we compute CVaR yet. So if I want to compute CVaR, essentially if I assume that the CDF is continuous at the var, which in our case it is, then my CVaR just becomes this formulation. So you have the scaling factor of the level beta, and then you can compute the expectation of the quantity of interest at the tail. So for x greater than the var. And now we want to define something of a risk region. So essentially it's very intuitive. You define this region where all the samples lie that are greater than var, and these are all the samples that are needed to compute my integral. Okay? And this gives us a little bit of a geometric interpretation. And we'll see in a second that we actually need that. So in the first part of the talk, I want to say we have a high fidelity model. This can be a, whatever you call your high fidelity model. It could be a analytic solution, it could be a high fidelity computational simulation, or whatever you choose. And then we have a reduced order model of lower fidelity that's very cheap. And now assume, this is the first part, we would have an error. For example, Gianluigi has talked this morning on how you can obtain error bounds for the for a certain class of PDEs, of course, with the reduced basis method. So assume we have an error bound here. What can we do with that? Eventually what we want is, I want to sample from the reduced order model, I want to compute a CVaR from the reduced order model, and I want to kind of bound the error of the CVaR to the full order model, whatever my full order model is, if I have this bound. You'd think this was possible, and in the next few slides I'll show you that that is. So now we define something that's called an epsilon risk region, which is in a sense a padded risk region that pads the risk region of the reduced order model with some sort of an error, with the error. And we'll see in a second how this is, how this graphically looks. Okay. So I would have the risk region here of my high fidelity model. So those are all parameters A and E that would cause a very high temperatures, and it would then lie in the tail of my CDF. And then I have my risk region that's indicated for my reduced order model 2, which you see looks a little bit different. But now when I do the padding, so when I know the reduced order model, but I also know an error, which I assumed I have, then I can pad this risk region with an error around, and so eventually I get this one. So now I have a padded risk region, which potentially, which contains this risk region, that's what we show in the lemma, and which is larger, but it's you'll need that in a second to actually compute CVaR efficiently. And so here I want to just introduce this max error. This becomes quite important. So this is the maximum error that you have in your padded risk region of your quantity of interest. So we'll kind of need that in a bit. It actually turns out that this error is all you need. You need the error in this padded risk region, and you don't necessarily need the error of the reduced order model everywhere, because you're interested in computing that tail with this approach. Okay. So now I just wanted to show how this would look for 4 different reduced order models. So again, risk region of our full order model. The risk regions you see actually as you refine the ROM, the risk regions are kind of getting better and looks more like the FOM risk region, although all of them are not too bad. And then you see the padded risk region. This one is much larger because you assume it has a much bigger error, so you have to pad it more. And eventually, as you go down, as the error goes down, also the epsilon risk region converges to the true risk region. Okay. So now you can show things like this. If you have an error bound, you can show that if you use your reduced order model to compute CVaR, the error that you make to the true CVaR is bounded by this constant, which is beta is fixed, and then the error that your reduced order model has, the max error that your reduced order model has in the risk region. Okay. And so, you know, if you're under a specific assumption, you can even get rid of this factor here, which is fairly benign anyways. So essentially what this theorem tells you is that you only need the error in the risk region, which gives you a little bit of an indicator how to build good reduced order models later. And I'll talk about this towards the end in the future work. Now we'll look at some numerics, how this works. So now I say here I have a maximum error over my entire parameter domain. I call this the max error, epsilon r max, depending on the reduced order model order. And I have a max error in the risk region, and I have a max error in the epsilon risk region. Here it turns out that the maximum error that you would have over your entire parameter domain turns out to be in the risk region too. But doesn't always have to be the case, but it's the case here. And now I show some CVaR estimates that we computed for this level beta is 0.95. And we've done this for different levels, but this is a reasonable level that people are interested in. And so you see here that the high fidelity model gives you a CVaR 53.94. First ROM was really bad. Second ROM and so forth. You see as the reduced order models are getting better, the absolute errors are going down. And then, of course, the CVaR error goes down too, because we have this nice error bound. So that's all nice if you have these good models, and most importantly, if you have the error bound. But it's tough to come up for nonlinear problems with a nice rigorous error bound for reduced order models. So now we said in the second part, well, what if we don't have that? Can we still use information? Because surrogate models contain a lot of information about your problem. But can you use it in a meaningful way? And how can you use it for computations? So in the second part, if we don't have this rigorous error bound, we're going towards something that's called a statistical estimation technique called importance sampling. And we have done some importance sampling work for failure probability estimation. This kind of motivated to use this as well for this CVaR estimation. Okay, so I just want to introduce this importance sampling in one slide. So you have what I would call a nominal density rho with a certain support in this big set. And then you have you want to find another density, which is phi, and which has a larger support than rho. And you want to do that because if you sample from your original density, it's very unlikely, if something is an extreme event or a rare event, it's very unlikely if you sample from the original density that your samples will lie in these small regions of parameter space. So in essence, you want to find a new density that's more likely to give you results in your risk region, for example. But of course, if it's more likely, you have to do some reweighting, because all of a sudden you get a lot of hits and you have to reweight them with the proper weights. So that's all this importance sampling says. I want to compute the expectation of a certain integrable function of my original density, and then if the support condition holds, I can do a change of measure. I introduce some weights, and now I can actually compute the expectation under this new density phi of the function I was interested in, multiplied with the weights. And those are called importance weights, or you can likelihood ratios. Okay. So for CVaR, we can do the same. We can just do a change of measure, and we can reweight. So I can compute CVaR just by, this is the indicator function in the risk region. So every sample that falls in the risk region is going to be counted and then reweighted by this weight function. And here we have to make this assumption that our biasing density so that the weights are well defined, that our biasing density has a larger support than the risk region here of the original model. Okay, so now there's a lot of stuff on this slide, but I think what I eventually want you to focus on is that there has been work for the value at risk and for the conditional value at risk to study asymptotic behavior as you sample, and those are kind of some of the sampling estimates applied to our methods. So if you do importance sampling, for example, for the value at risk, you get one of these results with a convergence rate of 1 over square root of n. And then if you do it more importantly, this is what we need. If you do importance sampling, if you have a finite sample importance sampling estimate of your conditional value at risk, then you have the following result. And you see that this is the interesting term now we need to look at, because ultimately you want to, so importance sampling now is trying to find, the goal of importance sampling is trying to find a density that gives you the right information of where your interesting regions in parameter space are. And in that case, you want to find the density that actually minimizes the variance or even sets it to 0. Now that's very ambitious, but that's the term we're going to have a look at now, okay? So ultimately, I'd like to find a density that makes this variance 0. Now, we can say that there's an optimal biasing density, and this is standard following approaches from Owen and other statistical work in importance sampling. You can say there's an optimal biasing density, and it looks like this. So it is defined on this risk region. It depends on the value at risk and depends on this conditional value at risk. And if you plug this into the variance term that we had before, you actually get 0 variance. Beautiful. So you have a sampler that with one sample gets 0 variance. Problem is it's not practical, and that's very well known in the statistical community. Because why is it not practical? Because it depends on exactly the quantities you're trying to compute. So it depends on CVaR and depends on VAR. So you can't use the density, but the density gives you, I mean, just writing it down, the optimal density gives you a feeling of where you should be sampling. So it gives you some intuition about it. And that's typically how it's done in importance sampling. You look at the optimal density and you're trying to approximate it as good as you can. So now, for us, we said, okay, the optimal biasing density, it can't depend on CVaR or on VAR itself. So let's drop these terms, and we start with an initial choice of this one. A problem here is still that it's still defined on the risk region of the true model, of the high fidelity model, which we don't have. I mean, we can't compute that. So now let's approximate that. As we have seen that there's a set inclusion, we have seen that our epsilon risk region is always larger than the true risk region. So now let's approximate that with our epsilon risk region here. And now we have a computable density that we can sample from. So that's going to be our biasing density from now on. So now we have a biasing density that we can use, and we can actually show that if we use this biasing density, we improve our, so if we use the biasing density, we improve our variance by a factor of the probability of our, or the size of our risk region. Okay. So this is comparing importance sampling with just standard Monte Carlo from the nominal density. And so the size of the risk region is 1 minus this beta, okay? Approximately 1 minus beta, because it's padded with an error, okay? So this seems to be a good biasing density that reduces our variance and that we can actually compute. That's the most important thing. So now here I have a few results that I want to show you. So now what do I need to do? I need what's called this epsilon risk region. So I need some indication from my reduced order model where it thinks that the tail behavior occurs. And so therefore I run 10 to the 4 ROM evaluations to explore my risk regions. Then I can define my biasing density as in the previous slide. So I can start sampling from this one. And now I have an estimator which actually uses only 100 high fidelity model evaluations. Okay? So I only sample 100 times from the high fidelity model. And then I get the following estimates. My reference is going to be this 53.94, which I computed from a lot of high fidelity samples. And then we have something that's mean average error and mean relative error. So you see that if I do importance sampling with a density that comes from, that I constructed from the first reduced order model, then my average CVaR is 54.02. And as I use better and better densities, meaning densities coming from better and better reduced order models, my mean average error actually goes down. So what that is saying, that also note that even though the first model was pretty much, I wouldn't use it to simulate and realistically and to get a good bound on the quantity of interest because it had massive errors, but nevertheless it was still able to indicate that the risk region for us well, in a sense that it gave us a good biasing density. I'm not saying this is always the case, but what we definitely see is that as we make the reduced order models better, the risk regions shrink, and therefore our biasing densities are getting better. And then we also see the variance reduction. So as we've shown, you can compute the variance reduction. It's bounded by this probability of the risk region. And you can see that we reduce the variance by using these densities that we propose, by these vectors, and then of course we have the bound on the right hand side, and everything on the left is always less than on the right, so we kind of showed numerically the statement of the theorem. Okay, and one thing you also notice, as your error goes to 0, meaning as your reduced order model becomes more and more accurate, the size of the risk region actually converges to 1 minus beta, which is 0.5. So you see it's getting smaller and smaller, and eventually gets close to that. So now maybe I just told you something nice to do, but maybe I skipped over the part of over some computational costs. I mean, one thing you have to do in reduced order modeling is you have to invest. So you have to invest some simulations, and whether it's a greedy approach or whether it's a POD approach, you invest some simulations, you get some high fidelity model data, and then you are able to find projection subspaces. Okay. So now you could ask yourself, well, you put all this money in a reduced order model. How about I just use all these simulations and directly sample from the full order model? Would I be better off? And the answer is actually no. It really pays off to go into to construct a reduced order model and then sample from it almost free. So here we compared just the situation where I build a reduced order model with 100 snapshots. So I have 100 solutions to my system, build a reduced order model. And then I use the reduced order model to importance sampling with another 100 samples. So essentially I used 200 samples, 200 solutions of my PDE or my high fidelity model. Well, I should compare that with a Monte Carlo run of 200 samples if I use the high fidelity model directly. Okay. And so what I see, for example, if I use a Monte Carlo run with 200 samples, my mean average error is 3.66. And before, if I go to one of these examples, for example, any of these important sampling densities has a mean average error that's much better than what I see if I directly sample from the reduced order model. And even worse, when you say, okay, well, let's back up. Why are you using Monte Carlo? Why don't you use importance sampling with the high fidelity model too? So use the high fidelity model, run it 100 times, identify your risk region, fit a density, and then do the same as you did before. Well, I can do that too, but the error gets even larger because 100 samples was not enough to explore that risk region. And so therefore, even computationally, from a computational budget perspective, it makes sense to invest in these reduced order models and then use them for efficient sampling techniques. And you kind of see that too. I mean, this is just one slide showing you kind of the 95% confidence interval, so kind of like the deviation in your sample. So I did 100 test runs here with the Monte Carlo with 200 samples, important sampling and so forth, and with model 2, model 3, model 4, and you can see how your variance really shrinks. Okay, so essentially I showed you a method that works both if you have a rigorous error bound or if you don't have a rigorous error bound. You can use these reduced order models if you don't have this error bound to do important sampling, and therefore you can get what we showed here, and some, hopefully I convinced you with the numerical examples. You can get some good important sampling estimates of CVaR. And finally, it does pay off to use your computational resources and build a reduced order model from what we've seen here. Clearly there's more work to do. I've given the introduction that this should all be embedded into a risk-averse optimization problem, which we haven't done yet. I've just shown you how I would compute CVaR in every iteration. And also it becomes apparent that the reduced order modeling error only seems to matter in these epsilon risk regions. So it gives you some idea that maybe some adaptive construction of a reduced order model that's particularly good in these regions is important, and that's something we're currently looking into. Okay, thanks.
Time for a few questions from the audience. Yes?
So you applied your important sampling in these simulated settings.
Mm-hmm.
Did you do it in any kind of applied setting? And then with that, then important sampling with any kind of sampler, there's always going to be a touchiness of what is the distribution from which you're drawing.
Right.
And I wondered what challenges you had with choosing the distribution in more applied settings.
No, I have not, so I have not faced the challenges, but I definitely want to look into more realistic data that I could use and where I don't have the nominal distribution. I fixed my nominal distribution just to be uniform, because that's what the people told us. We don't know much more about these reaction rates, so let's assume they're uniform between a lower and an upper bound. So that's what I use. But clearly, I mean, if you actually love to talk, if we can have some more realistic data we can use that on, that would be great. Yeah, and then I certainly run into other challenges. Yeah, good.
Other questions?
I was
Yes.
maybe I misunderstood something, but your reduced order model, I mean, that was extremely small. Is it true? You chose just
Yeah,
one.
yeah. So to say,
you have
it's
a
not-
multiple of just the one solution, something
Yeah.
like the mean or.
the one was kind of crazy. That the first one was only one POD vector, right?
Yeah, but it worked.
Yes. Well, the error in itself. So if you use the reduce, so this is the interesting part. It's what we're trying to get around and trying to understand. If you look at the model itself, and you look at the, where did I have? I have some slides about the errors of the model. Yeah, the first model has an error in the quantity of interest of about 800. Okay, so very large error. And remember, the quantity of interest, I think, eventually that's our quantity of interest. So it's the order of 70. So I mean, a massive error. But it turns out that when you compute it still thinks that those are still the values that are ending up in the tail. So in that sense, it gives us the right risk region. But then when we do importance sampling, we would not use this model to directly sample from because we would get a terrible bound. But if we do importance sampling, we're pulling samples from this risk region, but then we always ask the high fidelity model. We evaluate the high fidelity model on it. So that's the point you're making there. So as long as this model gives you a right indication where your parameters should come from, then you can have a good Bayesian density.
But is this an observation and you are surprised, or is this something that you expected? I mean, if I say that my model has an error of, I don't know, astronomically large numbers, I would say whatever I derive from that is garbage. But here, is it something that you could expect or would expect, or is this just observation?
I mean, we have not reached a definitive conclusion about this yet. So I wouldn't say, yeah, I guarantee you that. Just take a crappy model and you find no, for sure not. Yeah. So we still have to think about this a little bit more. Why this is the case? Yeah.
Did you test other problems, or is this the first one?
We tested this problem in various different configurations. Yeah, with different other parameters, like not just these random parameters, but different configurations of the inflow speed but I have not tested other ones yet. Yeah. Yes. Did that somehow? I mean, I definitely want to talk, but because that's kind of surprising to me too. Yeah. Yeah. Yes.
In these other tests, did you try more than 2 random variables? How far did you go in number of variables?
We have tried 2 random variables in these tests. Yeah. But you need to go higher dimensional. Yeah.
Yeah. So in higher dimensions, how would you this method? Do you have an indication of how this method would degrade?
No, I mean everything. Yeah, everything becomes much harder in higher dimension. The construction of your reduced order model. I mean, you need to sample in parameter space, right? So you need to think about some smart methods like Gianluigi talked about. So reduced order model construction becomes harder. Sampling becomes harder. Finding the right density and so forth, of course. Yeah. But I don't have an indication of how much worse it gets. Can't tell you that. Yes.
I think it's probably very important how that interplay between the reduced model and the high fidelity model
Yes.
works, right?
Mm-hmm.
And I mean, how automatic is that going to be? I mean, how does it kind of requires at this point a good human supervision, or?
Maybe I don't understand the question fully. The interplay between the reduced model and the high fidelity model.
You do something with the reduced model, you do something with the high fidelity model,
Right.
and you have to make decisions when you do
Right.
it. To what extent is it automatic? I didn't catch that.
Okay, so good. So in the first part, I would say if I have a good say I have a reduced basis method where I have a good reduced order model that I computed, and I have an error bound, I think it would be very efficient to just say, okay, I've already reduced basis sampling can be expensive. I've already invested all this time to reduce my error quite significantly. I would use that cheap model directly to sample from, and I get a bound on my CVaR.
Okay, that was, maybe I can make my question more precise.
Okay.
So because you said at some point it's not even important to get a good bound on your reduced model, but it seems that if you want to really control this, with some kind of guarantee, you need a bound on your reduced model, right?
Right. So in the first part you do, and in the second part, we've shown that even though this is that kind of going towards the same surprising thing, that even though my reduced order model wasn't good enough, it still indicated me the right region. And again, if you look at the importance sampler, what the importance sampler is doing, it takes samples from this. It was able to give me the right to direct me into the right parametric regions, the reduced model. But from then on, I never touch it again. From then on, I evaluate in my sampler always the high fidelity model, but I only need a few evaluations of it. So,
the quality of your risk region
right?
depends on the quality of the reduced model.
Yes. So your variance reduction, as we've kind of, where was my result? So your variance reduction will be kind of there. So if your risk region is very large, you won't necessarily, risk region is true risk region padded.
Yeah.
So if you have big errors, your risk region is large, you're not going to reduce your variance. But I also say if you have a bad reduced order model, you shouldn't expect good stuff. And so the fact that we got something good out is still something that's not clear to me. Yeah. So essentially you do importance sampling, but you're not gaining much.
That may be an important fact with higher number of parameters. Because then you must sort of reduce your region very effectively in order to have affordable sampling in the relevant region. I mean, just cutting a high-dimensional region by reducing by a fixed fraction, maybe the side lengths, it doesn't really do anything. You have still a high-dimensional region which you have to cover.
Right. Yes.
That's it, so.
Good point. Yeah. Thank you.
Then we can thank again Boris for this interesting talk.